Okay, let's unpack this. Imagine you're building a truly massive AI, what we call a foundation model.
Mm.
The kind that can translate languages, identify objects and images, even write creative text.
Yeah, they're the really big one.
Exactly. Incredibly powerful, but here's the catch. You need it to run everywhere.
Yeah.
From these huge supercomputer clusters with tons of resources,
Hmm.
right down to the tiny chip inside your smartphone. How on earth do you get that kind of flexibility, optimal performance on any device without having to train like a million different custom-sized models?
Which costs an absolute fortune, both in time and compute power.
Right. The reality today is that these powerful foundation models, things like Llama 2 or GPT-4, they usually come in fixed sizes,
Yeah, pick your side.
which forces developers into this really tough spot. Either you deploy a huge, accurate model that just won't fit on smaller devices, or you settle for a less accurate, smaller one.
Or, yeah, spend a fortune training specific models for every single scenario. None of those are great options, really.
Exactly. So today, for you, we're taking a deep dive into a really fascinating paper. It's called MatFormer, Nested Transformer for Elastic Inference.
Hmm.
And this research shows how one single, brilliantly engineered model can actually give you hundreds of accurate, smaller versions, basically for free. It's pretty remarkable AI architecture designed for what they call elastic inference.
Yeah, what's truly revolutionary here, I think, is that MatFormer directly tackles this fundamental deployment bottleneck. It completely shifts the whole way we think about it.
How so?
Well, it moves from pick a fixed model size to
Yeah.
adapt the model size precisely as you need it, and crucially, all from a single pre-trained model,
Okay.
which immediately brings up this really interesting question.
Hmm.
How can just one model truly hold, so many different configurations inside it? How does it give you that huge range of performance options?
Well, the name itself gives us a pretty big clue, right? MatFormer. It stands for Matryoshka Transformer.
Ah, the nesting dolls.
Exactly. If you've ever seen those beautiful Russian nesting dolls where each one perfectly contains a smaller version inside, well, you've basically got the core idea already. It's all about a nested sort of hierarchical structure. But here's where it gets really interesting. MatFormer doesn't just scale the whole model up or down. It actually introduces this nested substructure inside the standard transformer block itself.
Right. It's not just about having SML, XL models trained separately. It's baked into the architecture.
Precisely. It fundamentally re-architects the transformer to build in that scalability from the ground up. So
Yeah.
model size becomes this fluid, adaptable knob instead of a rigid, fixed choice. That's the real breakthrough here.
And if we connect this to the bigger picture, traditionally, if you wanted a smaller transformer, your options were kind of limited.
Yeah. What would you do? Pruning.
Right. You might prune parts after training,
Mhm.
which often needs more fine-tuning later,
Mhm.
or you just train a completely new, smaller model from scratch.
Which is expensive.
MatFormer's genius is building this scalability right into the model during the initial training. And the paper explains they primarily put this nested structure in a very specific, high-impact part, the feed-forward network block, the FFN.
Okay, the FFN block. Why there specifically?
Well, it's a strategic choice.
Yeah.
The FFN block actually dominates something like 60% of a transformer's total model size and also its computational cost.
Wow, 60%.
Yeah. So by optimizing and putting this nesting right inside the FFN, you get the biggest possible return on your investment, basically, in terms of saving memory and compute. It's the most effective place to build in this elasticity.
That makes perfect sense. So, okay, let's try to visualize this for you.
Yeah.
How does this nesting actually work inside the FFN?
Hmm.
Imagine the FFN block has like a certain number of internal connections, maybe DFM neurons. MatFormer cleverly organizes these connections so that for a smaller version of the model, it just plugs into and uses only the first subset of these connections, say the first M1 neurons. For a slightly larger one, it uses M2 and so on, all the way up to MG, which uses the full set, the full DF. It's about selectively using parts of a shared universal structure.
Exactly. Smaller models are true subsets of the larger ones.
And the paper gives the math for this, right? Section 3.1, equation 1, we don't need to read it out, but it basically says you use just the first part, the first M rows of those big weight matrices, W1 and W2.
Yep, that's the core mechanism. W10K just means use the first K rows.
Okay.
And ensures parameters are shared, which is crucial.
Okay.
And the paper really focuses on 4 specific granularities for the FFN, spaced exponentially, using ratios like 0.5, 1, 2, 4.
So what does that translate to in terms of size?
It means you effectively get nested hidden neuron sizes like DFF, DFF4, DFF2, and the full DF. Yeah. So right there you have 4 distinct sizes explicitly built into this one universal model. Small, medium, large, extra large, essentially.
And you mentioned the FFN is the main focus because it's, computationally dominant.
Right.
But is it only the FFN, or could this nesting idea apply elsewhere?
That's a great point. While the FFN is the primary target in this paper, they do mention the principle could potentially be applied elsewhere too, maybe attention heads, or even the token embedding layer.
Ah, okay.
This flexible parameter sharing design is really what makes MatFormer feel so, well, universal and broadly adaptable.
If you're looking at the paper, Figure 1 does a great job illustrating this. You can see the universal MatFormer block.
With the nested submodels and stuff.
Yeah, the MatLMs, ML, XL. And then it shows how you can combine them using their mix and match strategy later. It's a really helpful visual for understanding elastic inference, how one training gives you all these accurate submodels you can just extract later.
Exactly. It sets the stage perfectly.
So we've got the ingenious matryoshka structure down.
Yeah.
But the next big question, for me anyway, is how on earth do you actually train one model to be good at all these different sizes at the same time?
Right.
And make sure they're all accurate? It sounds incredibly complex. But the paper, section 3.2, describes a surprisingly simple, elegant strategy.
That's right. It's quite clever. MatFormer uses this random sampling approach during training. It doesn't try to train all the granularities, say, all 4 sizes simultaneously in every step. That would be way too computationally expensive.
Okay, so what does it do instead?
Instead, for each training step, it just randomly picks one of the nested submodels. Maybe the small one this time, maybe the medium one next time.
Okay.
And then it optimizes the model just for that specific configuration using standard methods like stochastic gradient descent.
So the loss function they mention, L-sampling, is just for the one size it picked in that step.
Precisely, L Merrill Y, where merrily is just the parameter set for that sampled granularity I. This is key because it allows the shared parameters, especially the ones used by the smaller models that are part of the larger ones, to get updated many times from different angles, you could say, across a training process.
Right, because training the large version also trains the small and medium parts it contains.
Exactly. And by default, they use uniform sampling. So each size gets roughly an equal chance of being trained, though they note you could probably tune this sampling for even better results. This whole process ensures those main G submodels, S, M, L, XL, are accurate. But crucially, it also sort of prepares the shared weights so you could extract hundreds of other accurate submodels later after training is done. And that's where the real magic, as you called it, comes in.
Okay, yeah, here's where MatFormer really delivers on that promise of hundreds of models for free. This is their mix and match technique, right? Section 3.3.
That's the one. So after training, sure, you can easily just pull out the S, M, L, or XL model by stacking the corresponding blocks. Simple enough.
Right.
But mix and match takes it way further. It lets you select different sizes, different granularities for each individual layer of the transformer.
Wait, for each layer?
For each layer. Think about what that means. If you have, say, L layers in your network and G granularities or sizes available for each layer, you can create G to the power of L different models.
Wow, G to the L. That's an exponential number of possibilities.
Exactly. An exponential explosion of configurations, all from just one single trained universal model.
So just to make that concrete for you listening, you could pick like the largest FFN block for the first layer, a medium one for the second, maybe a small one for the third, and just combine them.
Yep, you can mix and match across the layers.
And somehow these custom combinations, these models that were never explicitly trained in that exact configuration, they still turn out to be highly accurate. That seems almost too good to be true.
It does sound amazing, but the paper shows it works remarkably well. And they even offer a simple heuristic, a rule of thumb, for picking good mix and match configurations. They call it the least slope approach.
Least slope, what does that mean?
It basically recommends gradually increasing the subblock size as you go through the layers, or keeping it uniform. So you'd prefer configurations that maybe go from medium to large, rather than jumping wildly from, say, small to extra large and then back down to medium.
Ah, okay, so avoid drastic changes layer to layer.
Exactly. Keep the variation minimal or uniform. The intuition comes from how it was trained. Sampling usually picked one size for all layers in a step, and this simple heuristic turns out to work really well.
Oh, well.
The research confirms this approach performs just as well as, or sometimes even better than, using really computationally expensive methods like neural architecture search or NAS.
Right, NAS is where you basically have another AI try out tons of designs to find the best one.
Exactly.
Got
Super
it.
expensive. But with mix and match and this simple heuristic, you get that level of fine-grained optimization essentially for free at inference time. Zero extra computation needed to find a good configuration.
That's huge. And table 1 in the paper, that really puts it in perspective, doesn't it? Comparing MatFormer to things like OFSA and Dynabert.
It does. It highlights MatFormer's unique advantage. You optimize just a few base models during training, but you get this exponential number of models available at inference time.
And it clearly shows that nested structure and the power of mix and match, which avoids needing that complex post-training search that other methods often rely on.
Yep, it really emphasizes the efficiency and the flexibility you get.
So, okay, bringing this back to the real world, what does all this mean for actually deploying these models? It sounds like MatFormer is designed to handle, well, pretty much any situation.
It's incredibly flexible, yes, for what they call static workloads, where you know your compute budget up front.
Like deploying to a specific server or device.
Exactly. Maybe you have a latency target that fits a 40 billion parameter model perfectly, but the standard off-the-shelf models are, say, 34B or 70B. Neither is quite right.
Right, you're stuck choosing between too small or too big.
With MatFormer, you can just use mix and match to dial in a highly accurate 40B model, precisely fitting your budget, without any extra training cost. That's a massive saving in time and resources, avoiding that compromise.
Okay, that's powerful for predictable situations. What about unpredictable ones?
Even more impactful there, arguably. For dynamic scenarios, imagine your phone's battery's low, so compute resources drop. Or maybe the complexity of the user's query changes suddenly.
Mm.
MatFormer allows you to dynamically extract the optimal submodel size for each token or each query, adapting in real time.
That dynamic switching sounds amazing, but my immediate thought is consistency. If you're swapping model sizes on the fly, doesn't the output get, well, weird? Like, doesn't the smaller model sometimes give a totally different answer?
You've hit on a absolutely critical point.
Yeah.
Consistency. And this is where MatFormer really shines.
Yeah.
All the extracted submodels, even the mix and match ones, maintain really high behavioral consistency with the main universal model, the XL one.
Okay, so they tend to behave similarly, even at different sizes.
Exactly. This minimizes prediction drift. They measure consistency by checking if the generated tokens match, or by looking at the KL divergence, basically, how different the probability distributions over the next word are.
And why is that high consistency so important?
It's absolutely crucial for enabling these advanced inference techniques, like the dynamic switching we just talked about, or something called speculative decoding, without sacrificing reliability. You need the smaller models to act like faithful, faster approximations of the big one.
Okay, that makes sense. The paper then dives into experiments, right? Starting with language models, MatLM.
Yes, MatLM. They built decoder-only language models using the MatFormer architecture. And they didn't just compare them to standard transformers, they also compared them against adapted versions of previous elastic models like OF and Dynabert to make it a fair fight.
And they used those four sizes, S, M, L, XL.
Yep, based on the FFN ratios, explicitly optimize those four granularities. The models range from about 580 million up to 850 million parameters. Then they evaluated them thoroughly on validation loss and average accuracy across 25 different English language tasks.
And the results, were they good?
They were quite striking, actually. If you look at figures 2A and 2B in the paper showing the validation loss and the downstream task performance for the 850M MatLM, it's fascinating. All of MatLM's submodels, S, M, L, and XL, consistently outperform their baseline counterparts of the same size.
All of them. Wow, not just the big one.
No, even the smaller MatFormer models were better than standard transformers of the same size. It wasn't just a marginal win either. It was a clear advantage across the board.
How did it compare to the other elastic methods, like Dynabert and OFFA?
Dynabert, which uses a different training strategy, joint optimization, showed a pretty significant performance gap. The paper suggests its approach leads to fewer effective updates. It needed like 15% more compute to catch up to MatLM.
Okay.
OFA, while it has a universal model, kind of struggled at the extreme ends, the very small and very large sizes. Its performance curve was more bell-shaped, suggesting issues with the quality elasticity trade-off. Plus, OFA needs that complex, expensive NAS step to find good subnetwork.
Right, the extra search step.
Whereas MatFormer, just using that simple mix-and-match heuristic, consistently hit the best trade-offs between performance and compute cost, with absolutely no extra search cost.
Now, you mentioned speculative decoding earlier and how consistency is key. Did they test MatLM for that?
They did. And this is one of the coolest applications showcased. Remember, speculative decoding uses a small, fast draft model and a large verifier model.
Right, to speed up text generation.
The faster the draft model is, and the more often the verifier agrees with it, the bigger the speedup.
So consistency between the draft and verifier is paramount.
Exactly. And Figure 2C in the paper shows MatLM submodels are up to 11.5% more consistent with their own XL verifier model compared to baseline models used as drafts.
11.5% more consistent. That sounds significant.
It is. And it leads directly to speedups. Table 2 shows MatLM-based speculative decoding is up to 6% faster on benchmark tasks like Lambda and Trivia QA compared to using standard baseline models with the draft verifier pair.
And there was another advantage too, wasn't there? Something about caching.
Yes, because the draft, say MatLMS and verifier MatLM XL models in MatFormer share underlying parameters and structure, you can actually share the attention cache between them during decoding.
Ah, which you can't do if they're two completely separate, independently trained models.
Precisely. That cache sharing provides further efficiency gains and reduces the memory footprint, which is another significant practical advantage of MatFormer's nested design for this technique.
Okay, that's impressive. But one lingering question for any new architecture like this is always about scaling. Does it hold up as models get bigger?
A critical question, absolutely. Does the magic continue as you pour in more parameters and data?
Yeah.
So they explicitly tested this. They trained MatLMs from a relatively small 78 million parameters all the way up to 850 million. And the findings shown in Figure 3 are really encouraging. First, the largest MatLM model, the XL version, scales just as reliably as standard transformer LMs. Its performance improves predictably with size, following established scaling laws.
Okay, so the core architecture scales well. What about the smaller nested versions?
That's the even more surprising part. All the MatFormer granularities S, M, L, and XL follow similar scaling trends. Their performance also improves predictably with more compute and data.
Wow, so even the small nested model gets predictably better as the overall universal model scales up.
Exactly. The scaling law parameters they fitted, shown in Table 3, are remarkably similar between all the MatFormer sizes and vanilla transformers. It confirms this robust scaling behavior.
So you get all that amazing flexibility and efficiency of MatFormer.
Without sacrificing the well-understood benefits and predictability of scaling up large models, it's kind of the best of both worlds.
Okay, so MatLM looks great, but you mentioned it wasn't just language models. They also applied it to vision.
They did. Creating MatFormer vision transformers, they wanted to show the approach is general.
How did it do on standard vision tasks, like image classification?
Really well. On ImageNet 1K classification, the MatViT models either matched or in some cases even outperformed standard vision transformer VIT models of equivalent size.
Outperforms.
Yeah, especially for larger sizes like VIT L16, MatViT was up to 0.35% more accurate. And again, as Figure 4 shows, the mix and match models generated from MatViT fit perfectly along that optimal accuracy versus compute curve.
That's great. But where does the elastic part really shine in vision? Is there an application similar to speculative decoding?
There is, particularly for adaptive image retrieval. This is a really compelling use case.
Okay, image retrieval, like searching a giant database of images.
Exactly. Imagine you've encoded your huge image database using a very powerful, accurate, but maybe slow encoder, perhaps the MatViT XL model.
Done offline.
Right. But now when a user submits a query image or text to search that database, the query encoder needs to be super fast. Maybe it's running on their phone, or you need to handle millions of queries per second on your servers.
So you need a smaller, faster encoder for the query side.
Precisely. But here's the critical challenge. For the retrieval to work, the smaller query encoder needs to place the query in roughly the same spot in the embedding space as the large database encoder would have. It needs to preserve the metric space structure.
Meaning similar images should still be close together even when encoded by the smaller model?
Exactly. And this is where traditional independently trained smaller VIT models completely fall apart. If you train a small VIT separately, its internal representation of images is just too different from the large VIT used for the database.
So the search just wouldn't work.
Pretty much. The paper shows that using a standard small VIT as an elastic query encoder results in almost zero retrieval accuracy. It just can't find the right matches encoded by the big model.
Yikes. But MatViT.
MatViT is different. As Figure 5 brilliantly demonstrates, the nested MatViT submodels, like MatViT or ANGEM, do approximately preserve these crucial distance relationships, from the larger MatViT Excel model.
Ah, because they share that underlying structure in training.
Exactly. This means you can dynamically switch to a smaller, faster MatViT submodel for your query encoding. The paper shows you can reduce the query compute cost by 40%,
40%.
with only a tiny, negligible drop in retrieval accuracy, less than 0.5%. This is a genuine game changer for large-scale semantic search, enabling flexible, efficient, real-time applications that were basically impossible before.